Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Theodore from Business Review, and I will be your host. It's our pleasure to have PROMECON with us today, who will be presenting this webinar entitled Drift-Free Gas Monitoring in Power Plants. Today's guest speaker is Hans George Conrads, who is a CEO of PROMECON. Before we begin, I would like to welcome you to our webinar platform on24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you have received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box and click submit. We'll allocate some time at the end of the session to address any questions or thoughts that you might have. Please use the yellow help widget if you require any assistance, and you can move, resize, and maximize any of the windows to get a better view of the slides. But now, please allow me to welcome Hans.
Well, thank you very much for the kind introduction. I'm very happy to be here and talk about our measurement, digital drift-free measurement of gas flows. I heard that we have quite an audience here, and I think it is very interesting to address the fields of application that we have, which is not only power stations, but also other parts of the process industry. I think most of the guests today are from power plant background, and despite the fact that we are in a big change of or transition of energy systems worldwide, coal-fired power stations will be around for decades to come, especially in Asia or other parts of the world. And I think that it is very interesting to have a little bit deeper look into one of the most difficult measurements in these industries. So let's start off a little bit. Our company PROMECON is actually based in Barleben, which is in Germany, not too far away from the beautiful town of Magdeburg. We started in 1995, so our company has been around for quite some time, and we are specialized in the measurement for power, cement, waste to energy, and other smelter industries. So heavy industry with high temperatures and dust-laden flows is really of what we are specializing in. And especially the measurement and optimization of thermal processes is done with our measurement. And I'll be talking about that today. So let's just jump right in. Here's a brief review of all the industries we have served so far. As you can see, besides power generation, waste to energy, and steel, we are also very big in cement making, limestone, and then also non-ferrous processes such as lead, zinc, copper, but also the glass industry. To give you a brief overview of where we have been doing our business pretty much all over the world, this is a selection of our top 3 industries that we serve, which is power and cement, as well as steel. The green dots are power, the red ones are steel, and the gray ones are cement. So all around the world, we have been doing projects, and I hope that we can also serve you wherever you are in the world. First of all, I would like to talk about digital and drift-free gas flow measurement. Why is it important? Why are people so keen to have a measurement that does not drift in the process? And what are the specific problems that occur in the process that you have? Our measurement is used in very critical parts of the combustion as well as the post-combustion process. Here's a typical example for power industry. You see a side view of a large boiler with all the intake area of the coal flow, the airflow, as well as the gas flow. So our measurement here really is in primary airflow, in secondary airflow, but also in the gas flow to the electric precipitators. We can also measure flue gas on the left or the right-hand side of the precipitator. The main focus here, though, is really primary and secondary airflow, and I'll come to that in a minute. Also in the waste to energy business, we have huge problems in measuring airflow correctly. The big focus here is the primary air or the undergrade air that is distributed to the combustion zone in the grate or combustion process of the waste incinerator. On top of that, there's an interest to measure flue gas or the raw gas in and out of the scrubbers, as well as the gas flow to the stack. A very big field of measurement also is the cement industry. In the cement industry, you got most of the flows that are heavily dust congested, and wherever you are, whether it's in the milling process or the pyro process, whether you are on a downcomer or on a raw mill, there are many gas flows which are important to run the process correctly, to operate the fans at the ideal load point, and also to operate the fuel supply and other parameters. And they all depend on gas flow. They all depend on hot gas flow, which is mostly unknown because it's very, very hard to measure these dusty flows. Last but not least, a quick glance into the steel industry. Here we offer solutions for any part that is in the dedusting area, primary dedusting, secondary dedusting. And as the name already suggests, dedusting means that you have hot and dusty flows. In the steel industry, we even offer measurements for very hot gases right out the electric arc furnace or the BOFs. And we can measure gas flows up to 2000 degrees Celsius of gas temperature, also heavily dust congested. So to sum this up, PROMECON is basically a specialist in measuring dusty gas flows, drift-free and digital. So that's basically our field of business. Now, let's dive into the technical reasons. Why is our measurement so different from traditional measurements, and what is the main advantage of this measurement? In order to understand that, we would certainly like to look into a normal power station problem. And the most common problem is the air preheating of the power station. Every power station has a regenerative air preheater where on one side you have the flue gas coming down, heating up big masses of metal, which more or less turn around like in a carousel. And on the other side, you have the fresh air, which is pulled in and heats up in this air heat exchanger. But it also carries over a lot of dust from the ash of the combustion process. So all your preheated air in the power station has a dust burden. All of your preheated air is dusty, and therefore it's not so easy to measure. And what this preheated air causes as a problem can be seen in this picture. This is a typical arrangement for feeding air into a boiler. You have an air duct, you have a boiler, and then in between you have two things. You have a venturi, which is basically a flow obstruction in your duct that creates an additional pressure, what we call a delta pressure. And then later downstream, you have flap dampers, which you control by this measurement. And it's quite interesting to have a little bit deeper look into this. Why is this so important? When you have a venturi and you have a normal airflow, let's say 25 meters a second, you have preheated air with about 350 degrees Celsius, then what you see is that you have a typical differential pressure that you create by this obstacle of, let's say, 20 millibar. So you have a barometric pressure of, let's say, 1030 millibar, and then you create on that venturi an additional pressure drop of 20 millibar. And then using the classical flow equations by Bernoulli, you can then calculate what your flow is. So it is very important to measure the absolute flow on the intake of the venturi and then the flow in the throat section of the venturi. So you have two measurements and two legs, which then go to a differential pressure transmitter. And all you want to measure is 20 millibar. Now just imagine what happens by the dust and the heavy congestion of your gas flow if one of the two legs gets blocked with ash or blocked with dust. Then one leg basically cannot transmit the pressure anymore correctly. Yeah. So what happens then is you, on the other side, you still measure the barometric pressure, but on the blocked side, it is unclear what pressure will be able to get through. So if you have, let's say, 1,033 millibar, the normal pressure at sea level, what is the pressure that you can see on the other side? And this already makes the problem very clear. You start to lose absolute pressure differential. So you don't know what kind of pressure differential you're seeing at a certain velocity. And the consequences are severe. Your pressure starts to drift, so you don't see the correct pressure anymore that would be induced by the airflow. You also have delays in the transfer function of your pressure. So even if your system reacts, it reacts way too slow. And the result is that your damper control, which you can see on the right-hand side, right on the entrance of the boiler, your damper control is wrong. Your damper is controlled in a wrong way, so it sets the wrong flow values. And I'm going to show you examples of what the consequence of that will be. So this is the classical problem that you have if you're using conventional measurements. Now let's look into some values here. This is a typical problem if your instrument engineers see that you have a blocked impulse line. They send somebody out to blow it and to clean it. And this is a typical cleaning cycle that you see on this picture. There are two trends. One is the dark blue line, and the other one is the light blue line. The dark blue line is the delta pressure measurement. Now let's focus on that. The delta pressure measurement is very noisy and it's not very smooth. This is usually when an operator sees that there must be something wrong. Now he sends somebody down to clean it. You can see the point in time when this is cleaned in the middle of the picture. After that, the dark blue line is fairly flat line. So obviously something has happened and something gotten better. But let's look at the light blue line, the air damper position. Here you can see some issues. The air damper position before and after cleaning has changed quite dramatically. You can see the damper was in this position, and after cleaning it changed to another position. If you change the damper from one position to another, what happens with the flow? The only thing that can happen, the flow has to change as well, right? The flow has to change with the damper. In this picture, however, the flow is not changing with the damper. The flow is staying constant. What does it tell you about the correctness of the flow before cleaning? It's very clear. The flow before cleaning must have been wrong. But the operator could not see that the flow was wrong. The operator sees the same flow before and after. He only sees there's a little bit less noise. That's it. But the flow indication stayed the same. However, it's implausible. The flow has to change if you change damper position. You can see the same thing here, and it's very important to understand. This is a brand new boiler. You have the red line, which is the delta P, before and after cleaning. You can see the cleaning moment here. And you can see the flow is the same, only the big noise starts to go away. So you have a more noisy signal before cleaning than after cleaning. Now the blue line that you can see is obviously the damper position. Same thing here. The damper changes before and after cleaning. In this picture, it doesn't change from lower position to upper position, but from upper to lower. Now, which way the damper will change is completely unknown because you don't know which leg of your delta pressure transmitter was blocked. Now, on the bottom, you can see the yellow line. The yellow line is the PROMECON measurement, and the PROMECON measurement completely follows the feeder because the PROMECON measurement is digital. It will always give you the right value. It will never drift by getting more dirty. The measurement works like a digital clock. It has no drift. So with a digital measurement, you don't have the control problem that you obviously have with the delta P pressure measurement. And why this is, I'm going to explain in the next pictures. Now, before we go on to how the digital measurement works, I would like to mention a couple of other issues that you have with classical measurements. The first one I already mentioned 2 slides before. When your impulse line is blocked, you're not only getting the wrong delta pressure, you're also getting a delay in your pressure transfer function, which means if the pressure is changing, if the flow is changing, your delta pressure measurement follows very, very slowly. And that means that your control system is also going to overreact. That's the reason why you have all these noise. Yeah, you see the measurement is too low, you open the damper, nothing happens. You open it more, nothing happens. All of a sudden, the measurement comes up and then the damper goes down. And so it starts to swing and go about. And you can see this swing here, the typical problem of dirty impulse lines in a conventional measurement. Last but not least, a third problem that you can see with conventional measurement, and I'm going to talk about this later on in the presentation, but only have a look at this picture. This is a manifold of 5 airflows in a very large boiler. In the middle, you can see there is an airflow, and actually the airflow pattern, just for you to understand. In the lower half of the picture, all the air, this dark blue area, all the air comes towards you, and then it turns upwards. Yeah? So it turns upwards, and it also turns to the sides to reach the branches of the manifold. What you can see in the middle is that the air turns upwards with nearly no spin. So there is no swirl in the air. But if you look at the manifolds left and right of that, you will see there is a huge spin. There's a huge swirl. So all the measurements that are in these branches cannot measure correctly because the delta pressure measurement is set up for a non-swirl airflow. Any swirl will make your airflow measurement wrong as well. So that's problem number 3. We have 3 problems with the conventional airflow: the drift, the time delay by the blocked impulse line, and we have a problem with swirled airflows. All 3 of these issues we have killed with the new digital airflow measurement that we have introduced into the market. Now, let's have a look at it. This is how a system looks like. And you can see it's quite radically different from the delta pressure measurement. We don't have a single sensor, but we have 2. We have 2 sensors that protrude into the pipe, and these sensors are basically antennas that reach into the pipe. Now, let's see how this thing works. How does digital airflow work? First of all, the components. You have an electrostatic signal generation, which is basically nothing else than an antenna that reaches into the duct. In the duct, you have your dust, and the dust and the gas flow along, and the dust usually is your enemy. The dust is your problem because the dust congests your impulse lines. Here, you don't have impulse lines. You have an antenna that senses the electrification of the dust. So the dust becomes your friend. The dust, we use the dust as a tracer element to tell us how fast the gas is flowing, because the slip between dust and gas is only a few centimeters per second, and at a flow velocity of 25 meters per second, it's a negligible problem. So we are creating an electrostatic signal, and we're using that electrostatic signal to correlate then the velocity. So this is how it works. One antenna in the duct, you have your particles that are coming close to the antenna, and this generates an electrostatic signal. How is it? I mean, for everyone who is really interested in the physics, you have the antenna, you have Coulomb's law. So the antenna, let's say, has a neutral charge, then positive charge comes to the antenna. That means the antenna has now to have a negative charge because the total charge always needs to be 0. So as the positive charge flows by the antenna, you will have a negative charge on the antenna and then 0 again. So you will have a current, an electric current that you can measure on the antenna, and this electrical current will have the fingerprint of all the electric charge that flows by your antenna, right? So you have more electric charge, you have more fingerprint, and you get more signal. That's it. So you have a very characteristic signal on one antenna. Now with that, you can now do something, because you can put two antennas in a row. Yeah, you can see this here. It's called cross-correlation principle. You have antenna 1 and you have antenna 2. You have signal number 1 and signal number 2. And if you now take these two signals and make a cross correlation between them, so you just shift them all on top of each other, you will find the point in time where the match of both signals has its maximum. And this shift is the time of flight from antenna 1 to antenna 2. So let's have a look. These are the sensors, and you can already see here on this sensor a heavy dust load, a dust load that is not influencing our measurement. And why this is not the case, I'm going to show you in the next picture. Here, you have a duct with the two sensors, and the two sensors basically now generate a signal. As you can see here, this is our random signal that is created in sensor 1 and sensor 2. The particles are flowing by antenna 1 and antenna 2, and on both antennas they leave this what we call fingerprint. Now, as you can see with your own eyes, these signals are very similar. Yeah, they're not identical, but they're very similar. You can already see that. Now, if you put them on top of each other, you can see immediately, well, they're also time shifted, right? So you obviously have a time shift between the two signals. And this now becomes very powerful. These signals are non-periodic, they are very long, and they are like a fingerprint. So if you switch them in time and you do a cross-correlation function, you will find a function like this, where you can see a noise, and then in one point in time, you have a maximum. This maximum is the time shift of the signals towards each other. So in this case, for example, 52 milliseconds, right? So once we have that, we can immediately say we know the velocity of the signals, because, let me just go back one slide here. Because you have two sensors and you have a time shift of 52 milliseconds. Now, the sensors have a distance, right? And you know the distance. So if the distance is, let's say, 300 millimeters and you have the time shift, then of course, you can easily calculate the meters per second or the feet per minute, the velocity of these, of the gas flow. Now, I would say this is it. We're already finished. We have a distance, we have a time, and the time is a digital time. It's done by a digital clock, and the only thing that can drift is your time. Nothing else can drift here. Now, if you have a modern digital clock, the time never drifts. The time is always right. So we have now a measurement that cannot drift away, that will always give you the exact velocity that you're measuring. Yeah. So while you have the need to purge a DP measurement to give it back on track, and it will always drift away somewhere, the McON Air measurement will never drift anywhere. It will always stay where it is. So there is no need to recalibrate the system, because the only thing that we're doing is we're clocking out how fast the particles need from one sensor to another. It's a pure time of flight measurement. So we can measure up to very high temperatures. Important to note, the gas density doesn't bother us. Yeah. If you have a gas density of 1,000 degrees Celsius, you have very thin gas. To measure a delta pressure here is very difficult, just by the fact that the gas is very low density. Also, if you want to measure ultrasonic or with other measurements, you always have a very thin medium. For PROMECON, it doesn't matter. For a correlation measurement, the density of the gas is irrelevant. We have a dust load range from 0 to 3,000 grams per cubic meter. So we can start with virtually nothing, and I'm going to explain that later. We have a typical accuracy of plus minus 2%. Of course, we have to look at where we measure. If we measure inside a Venturi, we have good accuracies. If we measure just in a normal duct, we need a little bit longer run away from a bend, but you can achieve very good accuracies. Repeatability is king. The repeatability, I think this is very dear here. I think we're far better than the indication here. There is simply no repeatability issue. with this measurement. Response time 1 second, and then no K factors, no calibration, no drift, no pressure taps, no purging or cleaning. And this measurement is also available as a SIL2 according to EN 61508. So you can also use this measurement in safety relevant applications where you need the purging of the boiler, you have hazardous conditions that require a very low failure rate according to SIL2. Now, one more thing I would like to explain about the measurement of a vector. I've shown you this manifold with actually with the 5 branch-offs, and you could see that there was a lot of swirl in the flow. Swirl is one of the biggest issues in measuring airflow on large ducts. And I must say that you nearly always have swirl. As soon as you have a duct that has a bend in 2 dimensions, so it goes to the right and then it goes into the depth, you have 2 dimensions that you're turning, and already that is a screw type movement. Now your air has a mass and your air has an inertia. Your air always wants to go in a straight line. So the air will start to swirl counterclockwise or counterwise in order to stay in its inertia. Most of the ducts you are measuring have a swirl. Now, if you have a swirl, then the normal measurements fail. Why is it so different with our measurement? Our measurement is different because we have 2 sensors that are stuck into the duct in a perpendicular way. So let's say this is your true velocity vector that you see in the pipe. It flows from sensor 1 to sensor 2. However, it does not hit the 2 sensors at a perpendicular angle. It does not hit it at a right angle, but a different angle. Now, the velocity calculation that we do is always based on a sensor which has a right angle to both sensors. So this is the velocity that is the vector parallel to the longitudinal axis of your duct. This vector is completely what you would expect. So if you have a flow that is swirling, we're not measuring the swirl or the lateral movement of the air. We're only measuring the movement of the gas in the direction of your duct. Very important point. And that means that we are not affected by swirl. Yeah. So we've even done measurements on a burner barrel where we measure secondary air right on the burner barrel with 2 measurement sensors. And you can see, even if you have a big swirl element up front our measurement, the swirl angle will not affect our flow measurement along the barrel. And we could prove that in test rigs and in plants in a very impressive way. We're not affected by the swirl. Also in a stack, same thing. If you want to measure in the stack, most stacks have a big ID fan upstream. And the ID fan is usually an axial fan that is pushing out the gas flow in a swirl motion. You can also see it when you look at the plume coming out of the stack. Usually it's rotating when it comes off the top of the stack. So you have a swirl movement. How do you measure the correct gas flow in the stack? I would say most of the measurements cannot do it. Our measurement, again, has these 2 sensors. And even though we have a swirl, we are only measuring the vector between the sensors. And that, I think, is a very important point here to note. So we are measuring really what's going up the stack, and we don't care what's swirling around in the stack. So that's basically how we avoid a measurement error. Now, I would like to come to the point that I mentioned to you, dust loading. As I mentioned, we're measuring dust, and we're measuring electrified dust. Now, we can have a lot of applications where you do not have any dust, or where you have dust, but only in certain conditions. Let's say you start up a mill. You're purging the mill with clean air. So you open up the cold air damper all the way. Or you have in the steel industry a batch process that sometimes carries a lot of dust and sometimes doesn't carry any dust. What do you do if there is no dust? There's no dust. We have a technique in order to ionize the gas with a small discharge, a small corona discharge. So we have this lens inside the duct, and this has a small pulse that will ionize the gas, and these ionized pulses which you can see here on the lower left-hand side, will then be recorded by the sensor pair on the right-hand side. And since they are non-periodic, it will be very clear to see that you can correlate them on two sensors. And this correlation, again, will give us the very same result that you see without the ionizer. So with the normal dust, we have the same correlation characteristics than with an ionized gas flow. So you can see that we have a typical emitter charge. You can see that the two sensors as red and green, the red sensor and the green sensor, and they sense these two pulses. And if you make a cross correlation out of this, this is your cross correlation. Very clear, very clean. You can see very well how fast the pulse is flowing. And therefore, you can measure gas velocity. Same principle. Here's how this thing looks like. It's an emitter. You put it inside the duct. Where is it applied usually? In the cement industry, it's never applied. In the steel industry, it's also not applied very often. Most of the time, we have it in the power industry, for example, on pulverizers, but also on secondary airs when you do boiler purge and you go very, very low with your airflow. This, what we call range extender, has a very good property. It not only extends the range of dust that is allowed down to zero, it also extends the range of the lowest measurable flow. So with the range extender, we can start to measure with only a few meters per second. So we can measure very, very low flow. And that is why in the power station for boiler purge and other extreme situations, this range extender is the standard and is recommended by us to be used. So you have the range extender and the measurement system, and that in combination then gives you a reliable digital flow signal at all times. Okay, let's have a look at some of the technical features of this system. As you can see, we have two sensors, and the two sensors are then connected to the box. So what you can see here is the typical arrangement, full-blown, that you would see in a power station. You have the McON Air box, which has a PCB board that collects the raw signals from the two sensors. Sensor 1 and sensor 2 are at the top. You could also connect a temperature sensor to the box so that you can normalize the flow. So you not only have the flow velocity, but you can then multiply the flow velocity with the cross-sectional area of the duct. And then you can also compensate for the temperature, and you would use the normal barometric pressure at the plant level. We usually recommend that you take this temperature sensor and put it into the DCS system so that you take the direct velocity reading from us and you convert everything in your DCS system. The reason for that is that then every box and every sensor that you have out in the plant becomes 100% exchangeable. So if there any sensor breaks or you have any damage, you can take a box or a sensor, take them out, put a new one in, plug it, and then you are at the correct calibration all the time. Or I wouldn't say calibration, I would say compensation all the time. Now the flow diameter as well as the temperature compensation. That is all done in your DCS, and it's defined for each and every measurement location. So your DCS knows all these parameters, and all you're getting from us is just a simple flow velocity. On top of that, we have this range extender which comes upstream of the measurement. So you have a range extender that would constantly push out the extender signals, and then you can again measure correctly and have a drift-free measurement system. If you're using this system as an SIL2 system, so a safety integrity level 2 system, then every 2 years you need to do what we call a proof test. You have to prove that all the electronics are still working correctly, including a memory test and everything. This test is usually done by taking the power supply off the system, recycling it on, and push a button for the proof test. That's it. And if the system comes back on, then with all LEDs running perfectly, then you know you have passed the proof test. So it's very easy to do that. And if that's done every 2 years, you can extend the system's validity for SIL2 compliance on and on. So the motivation to install our system, just summed up, is what I've been telling before. You have an existing power plant. And let me give you some examples. You have, for example, a milling floor, and all the mills are showing different energy consumption. So you make a mass energy balance. You look at the amount of airflow over the mill, the amount of fuel through the mill, and you look at the delta temperature over the mill. And that allows you to calculate the amount of energy that is consumed to dry the coal. Now, if you have the same coal on all the mills, and the amount of energy that you need to dry the coal is different on every mill, well, then you have a problem. Because the mass energy balance needs to be the same on every mill. It's physics, right? Physics cannot be different. The thing is that the values that you're using to calculate your energy mass balance might be wrong. And the most common culprit is the airflow. The airflow is not correct. And if you calibrate the airflow, then the mass energy balance is correct again. So I can only invite you, if you have a power station, a boiler where you suspect you have an airflow problem, send us some typical DCS screenshots of your mills, of your secondary airs, of your air heater. We'll be easily be able to tell you if you have an airflow problem or not. And the airflow problem consists of the fact that you have implausible values for what your airflow is showing you. So PROMECON can analyze this. We can analyze the delta P problems. If you replace that with a more accurate measurement, you would have a much better mill control. You can also lower your overall O2 levels in the boiler. You can imagine if you have a large wall-fired or T-fired unit and the secondary airflows are different at all points, then you need to have a much higher excess air level to keep the CO down and keep all the unburned carbon problems away. If you adjust that to the same level at all burners, then of course you can lower the overall O2 level. You have a much better control and you save lots of energy. So that's basically the system. And we started the first installation, I think, in 2003 in a power station in Berlin. That was our first client. They had a big problem with boiler wall corrosion because they wanted to pull down on the airflow in order to minimize excess air and lower the flame temperatures. And the result was huge boiler wall corrosion. Now, the boiler wall corrosion was an immediate effect of an airflow measurement that was drifting away. So many burners were at the right stoichiometry, and some burners were way too low, and you had CO corrosion on the boiler wall. So with these customers, we installed our system and we converted from delta P to a digital measurement system. Some clients also started off with a digital system, but for example, this one here, this client is an Alstom boiler, 800 megawatts, also in Germany. They started off with a delta P measurement. You can see very well the Venturi section here on the right-hand picture. That's the outside view. On the left-hand picture, you can see the Venturi from the inside, and they had this problem. Even the data I've shown you came from this plant. They had this problem that the delta P flow would start to get noisy. They would send out somebody to clean the impulse lines, and afterwards the noise was gone, but all the dampers were at a different position. So we installed our measurement in parallel. You can see here from the inside left-hand picture, you can see there's a range extender, and then there's the two sensors that are installed. The outside picture you can also see very well. You can see the box that is mounted, which is the measurement box, and then the sensors that are inserted from the outside. And after we could prove our system right, they retrofitted the whole unit with our measurement. So we installed this on all the secondary airflows, on all the overfire airflows, and on all the primary airflows. We have installed quite a few plants in Germany, but also internationally, and they're using our measurements to control the boiler very successfully. And since we installed these sensors, we have not changed calibration. We have not been called out to recalibrate, retune anything. The sensors are simply running because the measurement is digital, and the answer will always be the same. There will be no drift away from this. Here, another plant. Very often we have this call from Chinese boilers. This is a plant in Turkey, in the region of Iskenderun. And this plant has a boiler, a Chinese boiler, tangentially fired unit from Harbin. And here you can see basically the cold air duct to the mill. We have retrofitted the cold air duct, the hot air duct to the mill for the primary air. And what you can see here is the header on the very left-hand side. And then as soon as the air branches off into the cold air duct, you have the range extender, and then you have the two measurements the two measurement sensors that detect the velocity. So here we could also very clearly prove that the measurement is very stable over long term, doesn't need a big adjustment, doesn't need drift adjustment. So it's also a very good measurement for anyone who has an issue with current maintenance and recalibration of sensors. We found that in many power stations, airflow is the most neglected measurement of the whole power station. And the reason for this is it's very tedious and time-consuming to recalibrate and retrim all these conventional measurements. In the cement industry, we even have clients that don't even know our measurement anymore because they never touch it. As it's always running, we don't have to correct anything. It just keeps on running, right? And it's always the same calibration. We never see any deviations. So that is a typical motivation for people to go over to our measurement. Here, another one that's in a power station built by Hitachi Power, a wall-fired unit. With this boiler, our system was directly specified by the final client who wanted to have a digital measurement in order to operate the boiler. We can send you a reference list with all the units that we have done over the past. We've done a lot of conversions from very drift-prone installations to absolutely digital drift-stable installations. So no big maintenance problems and no recalibrations necessary. Of course, our system fulfills the necessary certifications, the EC directive, especially the ones for the SIL2. And the system can be also used, as I mentioned before, for any application where you have a safety regulation. So where you have a safety integrity level as a demanded feature. Yeah? And we can do anything from up to SIL2. So SIL1 or SIL2 doesn't matter. Our sensors will cover that. So you can be sure that boiler purge, startup of the boiler, can be done in a safe condition, and our measurement will be correct and accurate in regards to what has been going through the boiler as gas flow. Maybe a couple of technical details for recapping. The measurement principle that we use is a cross-correlation principle. Yeah, that is quite unique in the world. There are not many cross-correlation measurements around. And as far as I know, there are definitely no cross-correlation measurements around in the power industry that can do SIL2. The measurement range is from 0 to 100 meters per second. I would say 0 is dear. I would say 2, 3 meters. We need a little bit of measurement velocity to start. But we can go, we say here 100 meters per second. The measurement principle can measure velocities that are far bigger than this. I mean, in fact, we could even measure transonic. But for boiler operation, I think anything up to 50 or 60 meters per second, that's the maximum that you would expect in a Venturi, maybe 70 meters per second in an airfoil, very, very tough, but that's it, yeah. But through all this, our measurement range is completely linear. We do not have, like the Bernoulli equation induced DP sensors, we do not have a squared relationship between anything. That means that our turndown ratio by nature is far, far bigger than the turndown ratio of delta P measurements. Because if you're wanting to measure 10% of the flow range, of the maximum flow range, with a DP transmitter, you are at 1% of the pressure level. Yeah. So the pressure levels go down dramatically. With our measurement, we have a linear time measurement. So if we measure 10% of velocity, we measure basically 10 times higher the time of flight of the maximum flow. So if we go down in velocity, the time of flight gets longer and longer, which makes our measurement even better. So I think a very linear measurement curve allows us a much deeper turn-down ratio. Typical accuracy plus minus 2%. If you want to know how accurate we can be on your application, please send us a drawing and we can show you an example, because we have to see where we can install our sensor in order to get a high accuracy on your duct. Repeatability, very, very high. There is simply no limits to drift stability. Again, cleaning, maintenance. Of course, you have to maintain these systems once in a while. If you have a large boiler outage, you pull the sensor out, you have a look at the sensor like you would normally do, but you don't need to have regular recalibration or cleaning of this. Gas temperature with the tactile sensors that you can see here, up to 1,000 degrees Celsius. The normal rated sensors for the power station in a secondary air environment would go up to, say, 400, 500 degrees Celsius. Minimum dust load, 10 milligrams to 2,500 grams. So there's a huge range. Should we fall below 10 milligrams or we have very low flows, we would recommend the use of a range extender. Yeah. Safety standards, SIL2, and then typical, the cover with NEMA 12 rating or IP66. Oh, sorry, NEMA 4 rating. That's why I was wrong here. IP66 or NEMA 4. And so that's basically it. The ambient conditions are typical for the ones in the boiler, up to 55 degrees C. Of course, the inside of the duct, we're up to 400 degrees C, as mentioned. What we can do is, if you have interest, we can, of course, send you spec sheets for our sensors. We have spec sheets for the sensors themselves. We also have spec sheets for the cabinet or for the range extender. So you can get, if you want, just send us an email. We can give you reference lists as well as typical spec sheets for this. One system I haven't talked about today is the infrared system. That is more or less a system for the steel industry that will be covered in one of our next webinars for the steel industry. With this system, we can measure gas flows up to 2,000 degrees Celsius of hot gas flow, but that's not so common in the power station applications. Maybe one day, but today I think I was talking about the main application: primary, secondary air, and also flue gas flow. Okay, that brings us to the end of this presentation. I hope I could give you a good insight into the system functionality and the contrast to the classical delta pressure measurement. So if you have any questions, I'll be happy to take them. Thank you very much.
Thank you, Hans, for the great presentation. I can already see we have a few questions. To all attendees, please bear in mind you can still submit your questions. And again, we'll try to answer as many as possible. But if we don't manage to get to all of them, your questions could be answered on a later date. Without further ado, the first question we have is, how often do you have to check the calibration of the measurement system?
Okay, I think that's a very quick one. The calibration does not have to be adjusted itself. The velocity measurement is calibration free, so you don't have to recalibrate the system ever. You don't have to do it over the whole lifetime. The only thing that you have to make sure, of course, is that the conversion is done correctly. So you have to measure the temperature of the gas in order to get the correct the correct standard temperature pressure STP flow, right? So in order to get the correct temperature corrected flow, you need to have the right temperature and you have to put in the right barometric pressure. That's basically it. That's all you need. And the rest is more or less free of any readjustment.
Thank you, Hans, for addressing that. The next question is a 2 out of 3 measurement necessary with your equipment?
That depends a little bit on the authorities. I mean, we've had a lot of boilers that we've done in Germany where a 2 out of 3 measurement is mandatory. And I explained this. In a typical delta P measurement, you are suffering from drift, and you're suffering from drift very often. So if you have 2 measurements and one starts to drift, you can see a discrepancy between the two. But which one is right? You don't know. So therefore, the authorities usually say, we would like to have a 2 out of 3. So you always have 3 measurements running. And if one starts to drift, there will be 2 more measurements that are not drifting. So there's at least a certain chance that you know which one is drifting. That's the reason for that. In Germany, indeed, the Deutsche TÜV, also the German authority, have dropped the requirement for 2 out of 3 for PROMECON measurement because our measurement is drift-free. So we even have power stations like in Walsum, I think that's a STEAG plant, where we, on a single secondary air burner with 100 megawatt of thermal power, one burner, 100 megawatts thermal, we have only one PROMECON measurement. The TÜV accepted that. So in fact, it makes a lot of life easier because you don't have to have so many measurements. Many power stations still use 2 PROMECON measurements because if someone cuts the cable or someone chops the sensor off, they still want to have 1 measurement left to run with. So that's maybe the answer to that question.
Thank you once again. Moving on to the next question we have. What is the expected lifetime of the sensors?
The sensors that we have put in 15, nearly 20 years ago now are still in service. So from our experience, it would be the normal lifetime you would expect, 15 to 20 years. Of course, some of the sensors may have a problem in the meantime if they're damaged, but the typical life expectancy, I would say, between 10 and 50 years, definitely.
Thank you. Moving on to the next one we have a few more minutes. How do I see that my current DP measurement system in my plant is not working properly?
Yeah, I've mentioned a couple of examples here, and I would like to defend the operators of the power stations here a bit, because very often the boiler does not have the correct airflow, and the operators have no clue that it has not the correct airflow. Because for an operator, it's not so easy to see that. Yeah. Let's say you have a boiler with 20 burners, and you look at 20 airflows. You can see all the airflows are the same. Yeah, you have so many tons per hour on this burner. You have the same airflow here, the same here, the same here. So all the same, and they're all running in a straight line. Would you, as an operator, think that you have a problem? Right? Now, if you look at the dampers, they look at the dampers, then you can see all the dampers are slightly different. But the dampers could also have a different angle on the axis. So you don't know what the real opening of the damper is. It's just a relative number. So even from that, you cannot tell that you have a problem. Only if you have a very long analysis and you can see that the dampers are starting to move back and forth and the airflow is not reacting correctly, you can have a guess. The easiest way to see if you have a problem is still the mass energy balance over your mill, so the primary airflow. You take the primary airflow, the delta temperature over the mill, and you take the co-flow. And out of this, you calculate the specific energy that is needed to dry the coal. If this is different in every mill vastly, and you have the same coal, you can have a first real suspicion that you have an issue here. You will have wrong input values into your mass energy balance calculation. And the most prone value is probably primary airflow. And the second prone value is feeder, but it's usually the airflow. So it's, again, if any of you clients have the suspicion you want to know, you send us a couple of screenshots from your DCS and say, can you check this for me? We'll be happy to do a cross-check, a brief one, and tell you, does it make sense or is your airflow implausible?
Thank you, Hans. I believe we have time for one more question. As we do compare with the DP measurement, which is impacted by non-laminar flow, how does the ionization of non-laminar flow will be perfectly captured with the sensors?
That's a good question. The ionization is not such a small thing, you know. If you actually what you have in your electric precipitator is very similar. They're called spray electrodes, and of course they have lots of kilowatts of ionization in order to make the collectivity of the ash better. So in your electric precipitator you have spray electrodes, and our ionizer is very similar, but it only runs at a very small power range. It doesn't have that much power. But the name spray electrodes says it all. You know, with the corona discharge, you really ionize a certain cloud, which expands very quickly because all the ionized atoms are repelling each other. So you have a certain cloud that goes over the sensors, and that cloud itself has a positive charge. So if it passes by a sensor, even in the vicinity of the sensor will have a negative charge, because if you again put the sphere around it all, the Coulomb's law applies, and the resulting charge must be zero. So it is not as sharp that it hits the sensor or it misses it. We have that sometimes in very long ducts, that if you have, you know, an ionizer and then 10-20 meters away you have your sensor. We have seen that in the past that sometimes we could miss the sensor. But in a power station application where we have 1 or 2 meters distance, we never miss the sensor. So it's a good question, but practically I don't think you have to worry about it.
I believe that's all the time we had today. Thank you, Hans, once again for the great presentation, and to everyone for attending this webinar. Again, you receive an email telling you how you can access the on-demand version of this webinar, which will be available up to 24 hours after the end of this session. And you can also check our website, which is www.pmi-live.com/events. We look forward to sharing further webinars with you, so please do keep an eye out on the website I just mentioned. Thank you all. Thanks to PROMECON once again for sponsoring this session, and hope you all have a great day. Thank you.
Thank you.